And now we have Kartick. He's going to continue to talk about the feedback-free starburst. You can get started whenever you are ready.
How do you change slides?
It's just a
Okay. So, good morning, everyone, and thank you very much for giving me this opportunity to talk about feedback-free galaxies in detail. I'm sorry, I have to stand here because the slide changer doesn't work. So, just excuse me for that. Okay, so just to recap, what we learned from Avishai's talk was that the basics of feedback-free galaxies, that you have to have different timescales matching certain density. So if I plot different timescales, for example, the feedback timescale, which is roughly about 1 million years, and above this timescale, the supernovae feedback will start working, and the free fall timescale will actually go down. So right around here, the density is sufficient that the gas can actually collapse into smaller clumps and form stars before feedback even starts. So these are typical timescales that we heard from Avishai. So one thing that I want to point out is that the feedback timescale is still about 1 million years. So this feedback will start working right after the first generation. So, right, as many pointed out, that it only is valid, this feedback-free regime is valid for 1 million years. But what happens after that? Because the galaxy virial timescale is right around about 180 million years. So the gas has to fall into the galaxy over this timescale, and this galaxy has to continue forming stars over this long timescale. And when the galaxy, this star formation happens at a much smaller scale, which is roughly about the gene scale, much lower compared to the whole virial size of the galaxy. So how does the galaxy continue forming stars for such a long time, even though it has gone out? I mean, supernovae feedback has started. So there are a few puzzles in this whole picture, which will slowly reveal. Is that one thing, that as soon as the first generation of stars form, we have winds. Okay, so each generation of stars will produce winds because of stellar. There is supernovae-driven winds, so it will lose mass as well as mechanical energy, and we can show that once all this mechanical energy is converted into kinetic energy, I mean, the thermal energy is converted to kinetic energy, the velocity of the wind will be roughly about a few thousand kilometers per second. There are certain dependencies here. So overall, what would happen is this picture of the wind that we would expect from a previous generation of stars. So radius versus different quantities. So we have the density, which is blue. So the density in a steady state, there will be a high density region where the star formation is happening, and as soon as you go out, the density falls as 1 over r square, because you want to conserve mass, and velocity is constant. And the velocity rises to a few thousand kilometers per second. This is a different parameter case, but you can see it actually already rises to 1,000 kilometers per second. The temperature is another quantity, which you could see that temperature is, the star forming region has very hot gas, but it's slowly, I mean, it actually falls quite fast as the wind expands, thus creating this very high velocity and cooler gas. So this temperature around here is about 10 to the power 4 Kelvin. So you have this high velocity warm gas expanding from this kind of star forming regions. On the other side, we have gas falling in from outside, mostly through streams, because the mass and redshift for these galaxies is actually where the cooling time of the shocks, virial shocks, are much smaller than the dynamical time. So a gas accretion happens through streams. And typical velocities are about 100 kilometers per second, Mach number of 15, and the density of the streams is about 10 particles per centimeter cube. So this density is not yet in the threshold density of feedback-free burst, so there will not be much star formation along on the way. However, what would happen is when these two things meet, okay, the feedback meets the streams. So this is a cartoon picture that I like very much. This is how I imagine that feedback and interaction of streams and feedback is happening in these galaxies. Okay? So we have different streams coming in from different directions, mostly 3 streams, containing most of the gas accretion onto the galaxy. There is some gas accretion happening through non-stream directions, which has lower gas fraction, but it has most of the volume. And we have this previous generation of stars that formed right at the center, and it creates this wind that I showed earlier, which the wind density decreases as you go out. And this wind interacts with this shell, or this stream, and stalls the shell. The stalling of the shell of the stream will happen where the ram pressures actually are comparable. The expansion of this wind in different other direction where the gas density is lower in non-stream directions are mostly following the wind-driven, the energy-driven bubble picture, and where we have this hot gas, internal shocks, all these typical wind-driven cases. But in this direction, in the streams, we have this stalling happening when the ram pressures match. Now, once the ram pressures match, we can calculate at what radius this ram pressures match. This is simply, we know how to calculate all these numbers, and this turns out to be less than a kiloparsec. Okay? Now, once this ram pressures match, we have this stream undergoes through shock. Okay? And given the density in the previous slide and given the density of this high, 10 particles per centimeter cube, it's quite easy to show that these shocks are actually isothermal shocks. So the density jump in the shock will be about, it's given by Mach square of the background density, which is simply 10 times Mach square is 15 square, which is right about in this few times 10 to the 3 particles per centimeter cube, which is actually just around the feedback-free regime. So this shell that we have actually can form, this is in the right feedback-free regime where fragmentation can happen and star clusters can form. Okay, so the fragmentation is, just to have if you have the density, it's not sufficient. What you need is enough mass over enough, small enough region. Because you can imagine you can have millions of solar masses, but spread across a whole tiny surface, thin surface, it would not work out that way. So what you need is right amount of mass within right amount of size. So what it gives is that you have to accumulate this mass as the gas falls in. So the accretion rate through different streams is about 65 solar mass per year. And you can show that it takes certain time for this shock to accumulate enough amount of mass such that it actually clumps, it becomes Jeans unstable. And by the time it actually becomes Jeans unstable, it actually accumulates through the whole surface, different streams, different shells, or shocks. It actually accumulates about into a 9 solar mass of gas for this entire period. Which is, so the whole gas is in this feedback-free regime. So what you can have is all these gas-forming stars right away as soon as they reach this Jeans instability regime. So we have one single burst which has this 10 to the 9 solar mass of stars, but provided this will form stars if they are not destroyed completely. So one that which I already discussed was that the radiation feedback from the previous generations, you can show that the shielding length for the radiation feedback, which is simply compare the recombination rate and the flux of radiation, and you get this thickness, which is very small. So the radiation feedback from the global star formation doesn't make much of a difference. Similarly, the main time scale in this picture, the hydrodynamical destruction happens around when the Kelvin-Helmholtz, over the Kelvin-Helmholtz time scale. And recently we have seen that it's actually getting very hard to destroy clouds once we include cooling, radiative cooling in these clumps or gravity in these streams. So both these things make it very difficult to destroy the clumps once they have formed or the streams. So the Kelvin-Helmholtz timescale is few million years, and this goes back to Andre's question. This is also the timescale over which the gas would mix. Okay, gas in the background, gas of the wind. This is the supernovae wind that will mix with the infalling gas. Okay. Now, if your feedback timescale is million years, much shorter than the Kelvin-Helmholtz timescale, you don't have enough time to mix all this hot metal-enriched gas to this incoming stream. So you are effectively keeping this incoming stream lower metallicity. So to keep continue do this feedback-free regime. Okay. Right. So okay. So this is the whole picture, how it goes. So you have infalling streams. We have supernovae wind from this inside. We have shell formation, and this clump formation happens within the shell. Then once the clump forms, we have star cluster formation. And once the star clusters form, they actually sink towards the center, right? Because they are no longer bound by they don't feel the supernovae wind ram pressure. So they sink through the center at the time scale of roughly 10 million years. So at this time scale, it rejoins the previous generation of stars, and this whole cycle continues, and then does it again and again. I can show that given at one generation we have about 10 to the 9 solar mass, so for 10 to the 10 solar mass stars, total 10 to the 10 solar mass stars, you have to just go through this cycle 10 times, and you finally have finally successfully converted all the gas of this galaxy into stars, effectively making efficient star formation in the galaxy. Okay, so the second question is part of the how do we really know that there is supernovae wind going on in this galaxy? So one way to look at it is actually look into this wind and see whether this wind can produce the signatures that we have been discussing today morning and yesterday. That one, so we know that once this star formation happens, it produces the supernovae winds, which have this very 1 by r square, very steep profiles. So the winds are high velocity, and it can have lower densities. So effectively, we can create this high velocity broad H alpha lines or other lines. Of course, these numbers were calculated for a different galaxy, which is MET2 type galaxy, but you can imagine the same thing happening for a FFB galaxy. Right. So if we want to look at this comes back to previous yesterday's discussion, like what does the BPT diagram look like in this winds, or do we have any signatures of it? So I just show in this plot what is the typical ions look like in these winds. So you can see the temperature of this gas is quite hot within this star forming region, but as you go out it decreases. So inside we have this hot X-ray emitting ions, and outside we have this warm ions like oxygen 3 and other similar ions. So this ion fraction is purely from the temperature of the wind. But let me convince you that there is more going on in this kind of pictures, that in these winds, if we want to really see whether like probe into these winds, the typical diagnostics may not work for the following reason, is that the winds expand. This is a typical, this is the poster picture of outflows. This is M82. We have this dynamical time where the gas cools, and the other time scale is the recombination time of ions. Okay, so if in any case, if in some case the recombination time is actually longer than the dynamical time of this wind, we'll have a serious non-equilibrium ionization scenario. So we cannot really use the temperature to infer the ionization or the emission of this gas. So this is actually true for many cases, for many high ionization cases for galactic winds. Lower ions, however, are not affected by the non-equilibrium ionization. They are more affected by the radiation field. Oh, thank you. Thanks. Radiation field. So this shows how the radiation field in the wind actually varies over time. So this is a spectra. This is a new kind of simulation that I did, where we have non-equilibrium ionization radiative frequency-dependent radiative transfer along with hydrodynamics. So this shows the in-simulation spectra of the diffuse gas just outside the star-forming region. So what we see is this typical OB stars hill. Okay, it ends mostly at 60 electron volt. But something happens which is not expected earlier, is that if we look back into our plot, over here we see that this hot gas, there is hot gas which is highly dense, okay, which has a density of roughly 1 particles per centimeter cube. So if you calculate the emissivity, it's very emissive in X-ray. So once we calculate that kind of emission, we see that the hot wind can actually dominate the radiation field around this regime where we have high star formation. Okay, so how far this is already, you can see 4 or 5 orders of magnitude higher compared to just a redshift 0 UV background. So it completely dominates the local X-ray radiation field. I mean, the exact amount depends on mass loading factors and star function rate, etc. But this is a serious radiation field that can actually completely bias all the ionization structures. And this is what I show in, let's say, if we look at the oxygen 3 ion fraction, what I show is in equilibrium, collisional equilibrium, or just some radiation field, you see this dashed and dotted lines. However, if we consider this extra X-ray radiation, we find this solid line which is actually seriously more ionized compared to any equilibrium situation or normal radiation field. So this can actually seriously affect how we see the galactic wind in BPT diagram or in emission. So this is something that we have been trying to do, but the challenges, there are many challenges of doing all these things. One thing is that we really need to do this on the fly. Means we have to do high resolution simulations with cloud level stellar feedback, global supernovae feedback, non-equilibrium ionization, full radiative transfer to actually account for all these effects and finally compare with these BPT diagrams or observed spectra in these galaxies. Having said that, I just want to conclude to say this kind of galaxies can form stars at very high rate for the entire lifetime, entire dynamical time. So just don't worry about supernovae feedback. Even if there is supernovae feedback going on in the galaxy, there are ways that the galaxy actually ignores or avoids the whole supernova feedback channel. So no worry about that. And the galaxy size actually can be calculated from the shell size where the ram pressures meet, and that always remains less than kiloparsec. And probably we can have high velocity cold gas in these galaxies because of this expanding winds. Okay. With that, I thank you very much for your attention.
Thank you, Kartick. Questions?
So these very high velocity, like order 1,000 kilometer per second galactic scale winds in your model, presumably there are like 3D galaxy simulations out there that account for all of the physics relevant to that model.
Not all.
Do people see these sorts of winds in their like 3D simulations?
Right. So we do see in observations, M82 has H-alpha gas, which is going out at 600, 800 kilometers per second. This is observed in M82 galaxy. The second thing is this feedback-free starburst galaxies are actually quite different from the normal starburst that we know, because in normal starburst what you have is a star formation, and then we have interstellar medium. So the wind can actually entrain more gas along with it, and there are a lot of other interactions. So these kind of simulations have been done in the literature, but the feedback-free star formation is in a scenario where we don't have much interstellar medium left, okay, because almost all the gas is forming into stars. So this is like a purely wind expanding into almost vacuum region. So we have this all very idealistic wind expansion. But the simulations that I mentioned was that one has to really consider the high redshift galaxies and very high accretion rate and interactions with winds. I'm not sure if anyone has actually looked into such high redshift and particularly this kind of scenarios. Once we do that, we will be very confident whether the FFB scenario actually works and it can reproduce all the observations or not.
Thanks.
Any other questions? In the meantime, we can get the next speaker to set up.
Yeah, very nice talk. The clusters that are falling back onto the galaxy that are raining out from this those are star clusters, is that right?
Yes, yeah.
Okay. What's the total mass there? Is it a significant contributor to the buildup of the halo, or is this like frosting on the...
No, it's about 10 to the power 9, which is roughly 10%, 5 to 10% of the total stellar mass of the galaxy.
Okay.
Yeah. So there are more complicated interactions going on. Like what I discussed was just the dynamical time for a given radius and mass of the galaxy. You can calculate this dynamical time, which is 10 million years. But there are more complicated interactions, like you have to consider the dynamical friction into account, how these clusters interact with each other. It's a bit more complicated than that. But roughly, you can get the idea of what would happen, that they would actually compactify over time, over this time scale.
Cool. Okay. Thank you.
All right, thank you. Let's thank Kartick again.